Okay, in this video I'm going to run through the questions for quiz 13, which is a revision quiz on SC13, a topic that you did at the end of year 10. It's on metals, transition metals, alloys and electroplating. It wasn't on your mock. You definitely have totally forgotten it and you will have to go back and revise it. It's not difficult, but there is content in there that you will have forgotten that you'll need to relearn. And then SC24 is what we're doing, well, next week really, on polymers. So this first question here is about an experiment that they're doing where they have taken a piece of iron, they put it in a boiling tube with water, and in one case they have racked the iron rod in magnesium. And what they're trying to do is they're trying to see which of the iron rods rusts. Okay, so rust is just the special term we use for the corrosion of iron when iron reacts with oxygen and water and forms iron oxide. And the experiment on the left, they've wrapped it in magnesium. Magnesium is a more reactive metal than iron. So rather than the iron reacting with oxygen, magnesium will react with oxygen, and that will protect the iron and stop it from rusting. On the other boiling tube, iron is not coated in any other metal, so there's nothing there to preferentially react with the oxygen, meaning iron will react with the oxygen and we should see rusting in boiling tube B. Again, you do also need water for rusting to occur, which is why they are placed in water. The first question asks you, why are we using an iron rod rather than stainless steel? So steel, FYI, is an alloy, and an alloy is a mixture of a metal and some other substance. In the case of steel, the alloy contains iron as the metal, and stainless steel contains chromium, which is another metal, but it doesn't have to be another metal. But in this case, you've got two metals mixed together. And when you've got stainless steel, the chromium will react with oxygen instead of the iron. So stainless steel won't rust because it contains chromium that will react with oxygen and save the iron from rusting. So in this experiment, we want to investigate rusting. If you're using stainless steel, no rusting can occur. You're not going to get any results. So that's why you're not going to use stainless steel. The next one, why are you not going to use a pipette? It's just in this particular experiment, the volume of the water isn't actually important. It's not critical because the volume of the water isn't critical. You don't need to use something as accurate as a pipette. A measuring cylinder will do. And these are the results that they actually see after a few days. So in boiling tube A, the appearance of the iron rod is unchanged and the magnesium starts to disappear. Okay, that's because the magnesium is reacting with oxygen. It's forming magnesium oxide, which starts to crumble and flake and disappears, but the iron will not react with oxygen. Whereas over here, when there's no magnesium, the small amount of brown deposit, that's rust because the iron is rusting. This one I think you'll be able to get from the mark scheme. This next one is another question about alloys. So alloys of gold are often used to make jewellery. You'll have heard of this, 18 karat gold, 24 karat gold. So the higher the carat, the purer the gold. But essentially they're alloys. And again, the reason you would mix gold with something else is to make it stronger. So gold itself, pure gold, is very malleable. And if you've got jewellery, so maybe a ring, you don't want it to completely bend out of shape, and therefore using an alloy of gold can be beneficial for that. So here they've given you the percentage of the metal. So if it's 18 karat gold, 75% of it is gold and 15% is silver and 10% is copper. If it's 24 karat gold, it's 100% gold. And explain why 18 karat gold is stronger than 24 karat gold. So essentially, if you've got something pure, so if I was to draw 24 karat gold, remember it's a solid because it's a metal, all of the particles are exactly the same size and they exist in really neat layers. If I drew 18 karat gold, you've got your gold particles, but then you've got other particles that have slightly different sizes and they disrupt the layers. So you've still got your gold particles, but those layers, this is not the best drawing in the world, but those layers are now disrupted. And if you were to take a hammer to this drawing that I've got here, because they are all in nice neat layers, if you hit it, the layers can just slide over each other. If you were to take a hammer to this drawing here, because the layers are disrupted, it's much harder for them to just slide over each other, and it makes it stronger. So in the mark scheme it says the 18 karat gold contains its atoms of different sizes, alright, because you've got gold, silver and copper, all of different sizes, and this disrupts the structure of the metal and prevents the layers from sliding over one another. So you can use a diagram or you can just describe that in words. And the next question is similar. Why aluminium alloys are stronger than pure aluminium? The same idea. different atoms of different sizes, disrupts the layers, stops the layers from sliding over one another. Another question here about alloy steels. So again, there are different types of steel. So stainless steel, I said, was iron and chromium, but some steels it's iron mixed with carbon. But if it's steel, it's always iron as the metal, and then it's just mixed with something else to stop the iron rusting and also to make the iron stronger. Blah, blah, blah. Iron fence can be galvanized when the layer is scratched, exposing. Yeah, so galvanizing is another way to protect iron. So you essentially coat the iron in a layer of something. So in this case, you're coating in a layer of zinc. And again, the zinc will preferentially react with the oxygen, and the iron beneath is protected. So they're asking you here, so you've got your fence, it's coated in zinc, the zinc is protecting the iron underneath, but then the zinc is scratched and the iron is exposed to the weather and the iron still does not rust, and the question is why. So if you've got your little fence here, there's my fence, and all of it is coated in zinc, but then you get this little bit that's scratched off and you're exposing the iron underneath, okay? Even though there's a little bit of iron exposed, there's still lots of zinc on this fence. And the zinc, again, being more reactive than the iron, will preferentially react with the oxygen. Even though that bit of iron is exposed, the zinc will preferentially, all of this zinc here, is going to react with the oxygen instead of the oxygen targeting this bit of exposed iron. So on the mark scheme, it says zinc corrodes. That just means that zinc reacts with oxygen easier in preference to iron because it's more reactive. And that's essentially all you need to say. The next one, why would you electroplate with gold? Why do you coat objects in gold? Well, it makes them look nicer. So if you have, I don't know, jewellery, you can't afford 24 karat gold, so it's mostly silver, but you can coat it in gold if you like the appearance of gold. Also, gold is really unreactive. If you think about gold's position on the reactivity series, it's right down the bottom. So if you coat a metal in gold, it's going to protect it from corrosion. The metal underneath won't be able to react with oxygen, and gold is so unreactive it won't react either. On the mark scheme, they will also allow cheaper than using solid gold. So if you've just got a metal and coat it in gold, it's much cheaper than if the whole thing were made of gold. The next question here is similar. This whole idea is called sacrificial protection. All right, so you've got a ship here. It's got a steel hull, but there is iron in that steel, and some steels the iron can rust. It depends what the iron is mixed with. So what they've done here is they've added these magnesium blocks to the steel hull. Now, if they coated the entire ship in magnesium, that would be incredibly expensive, but they don't need to coat the entire ship in magnesium. By just putting in these blocks here, magnesium is so much more reactive than the iron in steel. Magnesium will react with the oxygen, and even though the steel is exposed, the magnesium will preferentially react and the iron will be protected. So again, it says in the mark scheme, magnesium is more reactive than the iron that's in steel. So the actual metal in steel is iron. Magnesium is more reactive than the iron in steel. Therefore, it's going to react with oxygen, with water, and the iron will not. So it says magnesium has a greater tendency to form to form ions, or magnesium has a greater tendency to react instead of the iron because it is more reactive. In this topic, you've also got transition metals, and there's a few facts you need to know about them. Transition metals are very dense. Okay, they are used as catalysts, and they form coloured compounds. Okay, so there's 3 facts that you just need to learn off by heart about transition metals. Often used as catalysts, very, very dense, their density is high, and they form coloured compounds when they react. So if you think of copper sulfate would be an example. Copper sulfate, copper is a transition metal and copper sulfate is blue. So that's an example of transition metal forming a coloured compound. This here, they're talking about using iron as an electrode. If you were having a fuel cell or thinking about electrolysis, when we looked at electrolysis and we looked at electrodes, we saw there were 3 criteria. It has to be able to conduct electricity. Okay, iron can. It's a metal. It's got delocalized electrons, so that's not an issue. Electrodes should have a high melting point. Iron does. It's got a very high melting point. But electrodes should also be unreactive, and this is where iron falls down. Okay, iron will react. It will corrode. It will rust. Okay, they're all essentially the same thing, and it will form iron oxide. So on the mark scheme it says iron rusts, iron corrodes, iron reacts, but you have to say with the oxygen, with the water, and it's going to form iron oxide, or it's going to rust. That's why it's not going to be suitable. Platinum acts as a catalyst. State in terms of the position of the periodic table why we'd expect it. The only reason is because it's transition metal. Okay, we learned over here that transition metals can typically act as catalysts. Because platinum is a transition metal, it can act as a catalyst. They don't all, but they often act as catalysts. This is a polymer question, actually. A layer of PVC is used to surround the copper in electrical cables. Explain why it's suitable. So electrical cables, right? Copper is a metal, it conducts electricity, so I've got that in my cable, but I coat it in PVC as like the layer of plastic that you would get going around, you know, the lead of your iPhone charger. And the reason we've got it there is PVC doesn't conduct electricity, so you don't get an electrical shock. So you have to say PVC has a low ability to conduct or doesn't conduct, or it's an insulator, and therefore it prevents you from getting electric shock when you pick up your electrical appliance. The next page here, they're told you've got an alloy again, so you're mixing two metals together, in this case copper and zinc, and it tells you that brass is 70% copper, and that means that other 30% must be zinc, and they want you to draw this. Now it's a mixture of metals. It's going to be solid, so you're going to be drawing these particles as a solid. Copper and zinc, if you look at the positions on the periodic table, they're right next to each other, so there's not going to be a big difference in size. But what they want to see here is that you have got a 70-30 split. So if I was drawing copper, so 1, 2, 3, I'll throw in a zinc there. There's 4 coppers, 5 coppers, there's another zinc, there's another copper, there's another zinc. 1, 2, 3, 4, 5, 6, there, 7. 1, 2, 3, 4, 5, 6, 7. I've drawn 7 coppers, I've drawn 3 zincs, so that's a 70-30 ratio, and I've drawn it as a solid. Okay, so that's essentially all you have to do. But you shouldn't have perfect layers, because they are not the same atom. Actually, maybe my layers are slightly too perfect. But yeah, they should be mixed up together, slightly different sizes, so you don't have perfect neat layers, and you've got a 7-3 ratio between the two. The next one again is about corrosion. This, it's not something that you'll learn specifically on the course, but they're saying hydrazine reacts with oxygen, and they give you the equation, and then they said a metal in water corrodes faster than an identical piece of metal in the same volume of water containing dissolved hydrazine. So the hydrazine is protecting against corrosion. How? Again, if you've got something that's willing to react with oxygen, it will react with oxygen instead of the metal. And if the metal's not reacting with oxygen, it is not corroding. Okay, so again, it says the oxygen is being removed by the hydrazine is reacting with the oxygen, and therefore you don't have the oxygen needed for the corrosion of the metal. 47, you've got a chain, you've lubricated the chain with oil. How does that stop your chain from rusting? Yeah, because you don't want your chain to rust, so you put oil on it instead. And again, oil, because for rust you need water and you need oxygen, and if you've got oil, you get this barrier that stops oxygen and water getting to your chain. So oil acts as a barrier. It's not that the oil reacts with the oxygen and the water, it just acts as a barrier. It acts as a barrier so that the water and the oxygen cannot get to your chain and cannot rust your chain. Base can be made of steel. Explain why steel is a suitable material for the base. So, I mean, actually I was going to say the mark scheme is quite limited here. It is a metal, so that the base can get a little bit hot. The only thing that they accept here is that it's high density, so the Bunsen doesn't tip over, and that's the only thing that they accept on the mark scheme, which I think is quite narrow, to be fair. But yeah, it's very dense, meaning it's relatively heavy for the size of it, and that means your Bunsen burner is not going to tip over, and that's all that they have on that particular mark scheme. So that's chapter SC13. Okay, it's all about transition metals, alloys, and preventing corrosion. So make sure you've read over that. And then the next section is about polymers. I'm not going to go through all of the questions because some of them you will get very easily from the mark scheme. I'll go through this one though. Which of these represents the structure of the polymer formed from the monomer? So if I want to go from a monomer to a polymer, all I have to do is get rid of that double bond. And when I come down and look at the next answer, I always want to find exactly the same thing, but with no double bond in place. So exactly the same thing, but with no double bond would be B, okay? The only change is there's no double bond, and I've got my extended bond lines coming out the other side. They're shaken with, so dichloroethene and polydichloroethene are shaken, all right? Dichloroethene is an alkene, and if it's an alkene, it's got a C double bond C, and if it's got a C double bond C, it will decolorize bromine water. Polydichloroethene, you have to remember, once it forms a polymer, I know it still says ethene in the name, but you lose the C double bond C when the polymer is formed. So even though it's still called ethene, it's because it was made from ethene, but to join them all together, that double bond is lost, and if it has no double bond, it will not be able to decolorize bromine water. So what I'm expecting to see is that only the only the dichloroethene goes colorless. All right, so this one will go colorless, this one will not, because the double bond is lost when the polymer is formed. And the next one, on figure 5, draw a circle around the functional group in this molecule. So the functional group is the C double bond C, the alkene functional group. To be fair, they also allow you to circle the Cl, because that atom is also capable of reacting, but the one we've learned about is C double bond C, so that's the one that should be circled. Draw a section of polychloroethane showing 3 repeat units. All right, so when I'm drawing a polymer, all I do is copy exactly what they've given me. So I've got a H up top, bonded to a C, bonded to a H. I don't include a double bond, I just change it to a single bond, okay, and that is 1 repeat unit. They've asked me for 3 repeat units, so I need to draw the same thing again. H, H, Cl, H, and then I draw it again. H, H, and then Cl, and H. So I don't draw any double bonds, but other than that, I just draw this 3 times and connect them. The other thing you have to do to show it as a polymer is you need to have extended bond lines going on each side. Polymers are really long chains. We don't have space or time to draw the entire thing, but these bond lines represent that the polymer continues in both directions, and it is a really long chain. You get, oh my god, you get 3 marks for just doing that. So really valuable to be able to do that. The type of polymer, because you're starting with an alkene, it is called addition polymerization. Later we are going to look at condensation polymerization, but if it's starting with an alkene, it is called addition. That I think you should be able to do once you have a look at the mark scheme. The name, the substance A, don't be put off by the fact that it's not all in a straight line, okay? You have got 1, 2, 3 carbons in a row. It's just been kind of drawn up in the air, but it's still just 3 carbons in a row. So if I've got 3 carbons in a row, it's going to be prop, and because I've got a double bond, it's propene. Now you can call it prop-1-ene if you like, but even if you moved the double bond, you would just number from the other side. It would still be prop-1-ene, so the 1 is not needed, so propene is enough there. Substance B reacts with bromine in an addition reaction. So again, substance B, I know they've drawn it not all in a straight line, but it is just an alkene, and they want you to show the reaction. So when I react an alkene with bromine, you have to remember that bromine is diatomic, so it's Br2, and what's going to happen is you just redraw exactly what they've given you, but you lose the double bond. So I've lost the double bond, which means I initially have this, and then where I've lost the double bond, on one carbon I'm going to put a bromine, and on the other carbon I'm going to put a bromine, and that is complete. The next one, substance C, can be used to use as a monomer to produce a polymer. Draw a diagram showing the part formed from 2 molecules, which means I need to be drawing 2 repeat units. So this is substance C, okay? All I need to do is draw it, but without the double bond, and I need to draw it twice, because they've told me I'm going to show what forms when I have 2 repeat units. And it says to show it as a polymer. If I'm showing it as a polymer, I need those extended bond lines out to the left and out to the right. Give the name of hydrocarbon Z, okay? Don't be put off by the fact it's not in a perfect row. You've still got 1, 2, 3, 4 carbons in a row, so it's going to be buth. It's an alkene. I see the C double bond C, so I know it ends in -ene, and specifically that double bond starts on carbon number 2, so it's buth-2-ene. Okay, we always give it the lowest possible number, so it's buth-2-ene. The next part, complete the balanced equation if I react this with bromine. So if I react this with bromine, okay, so C4H8 is my buth-2-ene. Bromine is diatomic, so it's Br2. And if we remember, we just did it over here. All we're doing is adding these two together. There's only one product formed. Addition reactions only ever produce one product. So all I need to do is just slap this together. C4H8 Br2. I'm just combining the two together and I have my product. Draw the repeating unit of the addition polymer formed when hydrocarbon Z undergoes polymerization. Okay, so again, I'm drawing exactly what they have given me, but I'm going to be leaving out the double bond. Okay, so this is actually quite useful that they've drawn a little bit up and a little bit down. Okay, so I'm going to draw it exactly the way they've given it to me, kind of like that, okay? But I've left out the double bonds. I'm filling in my hydrogens down here. I'm filling in my hydrogen here. I'm filling in my hydrogen here, and I'm filling in my hydrogen here. All right, so I've just drawn exactly the same thing, but I've left out the double bond. And now I need to show that this is a polymer. So this is really, really important. The two carbons that were part of your double bond, they are the carbons that have to have the extended bond lines. It doesn't matter if it can't go perfectly left and right. If there's something in the way, you just need to draw a line going this way and a line going this way to show that this chain can continue in both directions. Now, to make this look a little bit nicer, you could move that right down here out of the way, move this right up here out of the way, and have this going perfectly to the left and perfectly to the right. But if redrawing it and moving things is potentially difficult, just draw exactly what they've given you, lose the double bond, and the two carbons that were part of the double bond each just have to have a long line coming out of them to show that it's a polymer. You're only asked to draw one repeat unit, so I don't need to draw it again. That's question 52. And then the final page, draw the structure of the monomer showing all covalent bonds. This is easier. When they give you the polymer, all you have to do is put the double bond back in. So you draw, again, exactly what they have given you. You do not draw the extended bond lines this time, and instead you draw the double bond back in. And that's going to be the monomer from the polymer.